Hello, we are going to continue with chapter 3, part B. Okay, so let's get started. I hope you're doing well. So let me get rid of my picture and start. So we are going to talk about rates of change and behavior of graphs and composition of functions. Okay. So let's get started. So in 3.3, I'm going to talk about rate of change of functions. So let's get to it. So let's do number 8 and 9. So what we want to do here is find the average rate of change of a function on the interval, and we're given two functions, and that's 8 and 9. So before I do those examples, I'm going to go through some examples to understand what we mean by rate of change, and then we go from there. So let's do that. Now, if you think of a function like, let's say, this function here. Well, let's call it a function now that we're at it. So let's say this function is f of x equals to x plus 1. So let's go to 1, 2, 3, and 4, and 5. Find this value. F of 1 is 2. F of 2, if you put 2 here, 2 plus 1 is 3. And 4, and 5, and 6. Now, what is the rate when we go from 1 to 2? How much does y values change? So that's basically the rate of change of this function from 1 to 2, and that rate is given by 3 minus 2 over 2 minus 1. It's like the slope the slope of the segment connecting these 2 points, 1, 2, and 2, 3. So the rate is 1 over 1 is 1. What's the rate here? Well, 4 minus 3 over 3 minus 2 again is 1, right? So from 2 to 3, from 3 to 4, from 4 to 5 is always 1, right? Is always 1. So 5 minus 4 is 1, so 4 minus 3, 1 over 1 is 1. So the rate of change remains what? Remains 1. It doesn't matter where you are, what x values, the rate of change is always 1 unit of y over 1 unit of x. That means if you change x 1 unit, y changes 1 unit, right? Now let's compare it to this function. X squared. So let's say x squared plus 1. So we go through 1, 2, 3, 4, 5. So f of 1 will be 1 squared plus 1 is 2. F of 2 is 2 squared plus 1 is 5. 3 squared plus 1 is 10. 4 squared plus 1 is 17. 5 squared plus 1 is 26. Now what is the rate here? Well, 5 minus 2 is 3. 2 minus 1, 3 over 1 is 3. What's the rate here? Well, 10 minus 5 is 5 divided by 3 minus 2, 1. That's 5. And what's the rate here? From 3 to 4, that would be 7 over 1. And what's the rate here? 26 minus 7 over 6, 5 minus 4. So that's what? That's 9. So notice that here the rates were 1, 1, 1, 1, and here the rates are actually increasing. So functions that are linear functions, their rates remain the same. The rate of change remains the same. And in fact, the rate of change of this function is nothing but the slope of that, which is 1 right here. But the rate of change of functions that are not linear is trickier. In fact, that's what calculus is all about. Calculus is about finding rates of change of functions that are not linear, right? Because it changes. So if somebody asks you, what's the rate of change from 1 to 4, or from 2 to 3, or from 3 to 5, you can always say is 1 unit per unit. So let's go from 1 to 5. From 1 to 5 would be 6 minus 2 over 5 minus 1, which is what? 4 over 4, which is again 1 over 1, or 1. So the rate doesn't matter between what 2 points is the same. But over here, we can't do that. So if somebody says, what's the rate from 1 to 4? What's the rate from 2 to 5? Well, we can't say the same number, it's different. For example, what's the rate from 1 to 3? So from 1 to 3, the rate is 10 minus 2 over what? 3 minus 1, which is what? 8 over 2, which is 4, right? Now, the question is, how do we find the rate at a number? So if somebody says, suppose this line is like the line is the velocity of a car. So if somebody says, if you're standing right here and this car that is going that fast passes by you, how fast does it go when it gets to you exactly at that moment? How fast is the car moving? Well, you can say 1 unit right here, because the rate of change is 1 unit. And if we talk about the rate of change of distance over time, that's velocity. So it says 1 unit. So it's easy to answer. You say, since the rate doesn't change, or rate is always 1 unit. But over here, we can't do that. If somebody says, what's the rate at 2? Well, is the rate at 2 3 or 5? Right? Coming in, their average is 3. And I mean, the rate that we find between 1 and 2 is 3. And between 2 and 3 is 5. So which one is it? Well, we can't really tell. So what we can do with these kind of functions is to find the average rate always from a number to a number. We cannot talk about the rate exactly at 3 unless we know calculus, which we don't because this is college algebra. So in college algebra, we find the rate of a function this way. Let me go down a little bit here. So right here. So the rate of a function, let's say we have a function, and this function is changing, it's just going up and down like that. Let's call that f of x. So if I want to find, for example, the rate of change from a to, let's say, b, then all I have to do is find the y value here, which is f of a, and the y value here is f of b. And I find the slope of this line, this segment that connects these 2 points, and that slope is the average rate of change. Average rate of change of f of x from a, let me write it here, from a to b. That equals to f of b minus f of a is like y2 minus y1 over x2 minus x1. In this case, x2 and x1 are b minus a. This is a b here. Okay, so this expression is average rate of change between 2 numbers. All right, so let's now do this problem. It says find the average rate of change for 4x minus 2 between 3 and 3 plus h. it doesn't matter what this is, we use the same formula. So the formula is f of b minus f of a over b minus a. Now here a is 3 and our b is 3 plus h. See that? That's a and that's b. Okay, so we just substitute here. Now f is 4x minus 2. So what is f of 3 plus h? So we have to do f of 3 plus h minus f of 3 and then divided by 3 plus h minus what? Minus 3. So this is just h, right? So the numerator is going to be f of 3 plus h is 4 times the input minus 2. And the input is 3 plus h. And then minus, that minus right there, f of 3. Now f of 3 is 4 times 3 is 12 minus 2 is 10. You just put 10 there. We don't have that to be that long. So, and the denominator is just h. Remember this, these two cancel. So what do we get? We get 12 plus 3h minus 2 minus 10 over h. And if you simplify that, you end up with what? You end up with 4h. That's why did I put 3h? I don't know why I did that. Okay, 4h. Because that's 4 times h, okay? Okay, so we end up with what? The 12 minus 2 is positive 10, cancels that 10. So we get 4h over h, and the h's get cancelled. So we get just 4. And h cannot be 0 because we canceled it here. Okay, and number 9, well, number 9 is just more algebra, right? Nothing to it. So here's the function, 2x plus 2. So we're going to have to find f of x plus h minus f of x, right? So I'm not going to rewrite it because it's right here. So that's f of x plus h. And this denominator is actually x plus h minus x. So you just get x, right? And you just get h. Okay, so what's f of x plus h? You have to substitute x plus h for x and plus 1. So this whole thing is f of x plus h. And then the minus here is the minus from the formula. And then the f of x is this whole thing. We put it there. So this is f of x. And then we have to distribute the minus. And then we have to expand x plus h squared, which is h squared plus 2xh plus h squared. And then we have to distribute the minus 2x squared minus 1. And if you multiply by 2, that would be 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1. That's the numerator right there. So the 2x squareds go away and the 1's go away. So we end up with that right there. Right? 4hx plus 2h squared divided by h. You can factor the h out of here and then cancel it. So that's what we get. Alright, so that's average rate of change. We cannot find exact rate of change at a given number in algebra, but we have a trick in calculus and we can do that. Alright, so let me, I did that already. Alright, so let's go to number 16. So let's do number 16, see what's on 16. So number 16, we have a graph, and what we are supposed to do is from the graph we have to estimate the average rate of change from 1 to 4 from the graph, right? So let's do that. So we have to do that from what? From 1 to 4. So when x is 1 right here, y is 5. So that point is, let me change color so you can see it better. So we got 1 and 5. So that's 1 point. And then we have 4. So at 4, the y coordinate is right here, right? So 4 is actually 4 and 4, right? Now if you connect these two, you get a segment, and our job is to find the slope of that segment is the average rate of change, right? So the average rate of change here would be f of 4 minus f of 1 divided by 4 minus 1, which is, what's f of 4? Well, f of 4 is 4 minus f of 1, which is 5, and then over 4 minus 1, which is negative 1 over 3, right? That means for every 3 units from 1 to 4, for every 3 units of change to the right, on average we had 1 unit change in y downwards, right? And that's number 16. All right, so let's do the one other one. Let's see which one. We go to number 19 and 26, but what do we have to do? It says for the following, use the graph to estimate the interval on which the function is increasing or decreasing. Okay, so let's do that. We want to do 19 from the graph. Here we go. So now what is this business of increasing and decreasing? Well, when a function is increasing, so let's see, here's the coordinate plane. We have the graph of a function, and suppose the function is doing this, right? So what we see here is that as we go from left to right, that means when x increases, right? When x increases, increases from left to right, what happens with the y coordinates of the points? You see? So here, all the way to that point, here are the x coordinates, right, of these points. So what happens when x coordinates get bigger and bigger, larger and larger? What happens with the y coordinates of these points? Well, looks like the, oops, I erased it by mistake, but that's okay. So it looks like what happens here is that the y coordinates of the points, as you see right here, the y coordinates get bigger and bigger. As the x coordinates get bigger and bigger, y coordinates gets bigger and bigger. If that happens, we say the function is increasing, right? So in this case, I redrew the function as a function that is always increasing. Now, what about if a function is, let's say, a function is decreasing, like, let's say like this. So if you have a function that increases and then decreases and increases again, right? Then from here, from this point on the x-axis to this point on the x-axis, we say from here to here, the function is increasing. So when we say the function is increasing, where is it increasing? We mean the x-coordinates. And then the values of the function itself, of course, the values themselves, they increase. But that's not what we mean when we say find where, right? Where is the function increasing? In what interval? In what interval, right? What interval? Well, interval here refers to the x intervals, right? And that's all there is to it. So these points are called the relative maximum, and this is a relative minimum, or local maximum and local minimum. So local because around here, that's the biggest function value, and around here, that's the smallest function value. That's why they're called local or relative max and min. Okay, so now that we know what it means to be increasing or decreasing, so in what intervals this function is increasing? Well, it looks like right about here, which is in the middle of -2 and what? And 3, right there, right? So between -2 and 3, so if you go up, right about there, right? So from, and this arrow means what? That means this thing is going to go to infinity this way, and eventually it's going to cover all the x-axis here to the left. So from -infinity to this number on the x-axis, which is -2.5, this function is increasing. Now we never include the numbers. When we include the intervals, we don't put the numbers because at a number, a function cannot be increasing or decreasing. So we don't include them. So we say from -infinity to -2.5, the function is increasing. But there's also this area, right, this point right there, from here, which is 1. So from 1 to infinity also, the function values are increasing. So we put a union in between. When we have two parts of the domain where the function is increasing, we can put a union. Okay, so that's the answer to number 19. Now let's look at another example. Let's look at number, well, we don't want that. So let's look at number 26. It says the table below, so let me get it so we can write on it. So it says the table below gives the annual sales in millions of dollars of a product from 1998 to 2006. So here's the sale in 1998 and so forth, right? Now, what was the average rate of change of annual sales from 2001 to 2002? So from 2001 to 2002. So between these 2 years, how much the sales increased on average, the rate of it. Not how much the sales increased, but how much per year. So we're going to have to basically take these two as 2 points. So 2001, the sale was $243 million, and at 2002 it was $249 million. So these are in millions, right? So we have, this is like 2 points, and these are the y values. So this minus this over this minus this. That's what we get. And it's $6 million per year, right? Because the unit here is 1 year. So it's $6 million per year. That was the average rate of increase. Between 2001 and 2004, it looks like is 249 again, because the sales are going up and down, right? So 249 minus 243 divided by 204 minus 201, 221, I mean. And we're going to end up with about, you know, what is it? Well, let's see what we get. So we get about, got the answer hidden here. So we get about 6/3, so it's $2 million per year, right? $2 million per year, right? The average rate is $2 million, but the unit of it is $1 million per year. It was $6 million in 3 years, right? So it's $2 million per year. All right, so let's do, oops, over 26 we did. Okay, let's do one more and then we look at something else. So let's do 35, but our VU is off a little bit. So let me see if I can. I'm gonna go to 35. We get the 30. Oops. Here we go. So technology says for the following exercise, use a graphing utility to estimate the local extrema. Now, extrema is a word that means what? That means either minimum or maximum, right? So we have the word minimum, we have the word maximum, right? Maximum, and we have the word extremum. Now these are all singular, and if you want to make a plural, you just say minima, and then maxima, and then extrema. So extrema is actually plural for extremum, and extremum could mean min or max. It depends on the context. Okay, so here what we have to do, we have to graph this with the calculator and find the min and max. So let's do it. How do we do that? Well, first we have to go to y equals 2 and put that function in there. X to the 4th, so this is x to the 4th power minus 4x to the 3rd power plus 5, right? Okay, now let's go to zoom 6 first and see if you get a good picture. That's the standard. Not bad, but notice that we can't see this min, so let's go down a little bit more. Let's change the window, and instead of y minimum to be -10, let's make it -20. See if it looks better. A little bit more, and then we go we can come, the right hand side is too much, so I'm going to change this to maybe 5 or 6 and then make this maybe 30. So I want to make this maybe -30, and then y x max, maybe I make it 6. There. So it says find the use a graphing utility to estimate the local extrema of each function and estimate the intervals on which the function is increasing or decreasing. So it looks like this function is kind of decreasing to this point and then increasing after this point. If we can find that, then we know from -infinity to this point the function is decreasing. See that part right there? That's actually decreasing. So it looks like kind of like this, right? So it's decreasing all the way to this point. If we can find the x coordinate of this point, then we can say from negative infinity to that number, right? Union from that number to infinity. Now what's that number? Well, we have to find it with the calculator because we don't know calculus, and in algebra we're not going to be able to find that number exactly using algebra. We have to know calculus. But instead of calculus, we use calculator, okay? So let's do that. So let's see, so we go on the graph, we're gonna go to second, calculate, and you see minimum here, we're gonna pick number 3. Now the calculator, of course, is not gonna look from negative infinity to infinity for minimum. That's a lot of work and impossible to do. So it's gonna ask you, where do you want me to start and where do you want me to stop? So we're going to bring the cursor right to the left of this min. You see left, where is the cursor right now is at -2, and since this function is way over there at -2, you don't see it. So we're going to bring it to the right. See it? It's going to show up right there. You see it? So we're going to bring it to the right and put it right about right there, right before that point, and press enter. Then we move it past that somewhere and then press enter, and then one more time enter, and we got it. You see, is at 3, so x is 3. We don't care about that y, we care about the x. Now that y is the minimum value of the function at that point, right? In fact, in this case, it looks like it's the global minimum. That means for the whole domain of the function, that's the smallest value. It is also a relative one. Around here is the smallest value. Okay, so that means we found our number there. So that's with the use of calculator, right? So it's why do I put union here? So it's decreasing, right? My pen is not writing. Here we go. So it's decreasing here and is increasing here. I don't know why I put union. So increasing here and decreasing here. All right. All right, so that is our 3.3. Okay, so now let's look at the other section, which is 3.4, which is about composition of functions. Okay, so let's look at that. Now, composition of functions means basically operations with functions, and one of the operations that we do with functions, that is we don't do with numbers, is called the composition. So let's do number. Let's make this a little bit, first of all, bigger. Let's make this a little bigger. Oh, that's too much. Here we go. And now, so number, we're going to do number 5, and let's do number 5 first. So it says what? For the following exercise, determine the domain for each of the function in interval notation. Now, before I do that, let me explain how this works. So there are some operations that we apply to numbers: addition, subtraction, multiplication, and division. So for example, 3 plus 5, 3 minus 5, we can do that, right? 3 divided by 5. And we can do the same operations with functions. Let's say I have a function that is, x, and then I have another function, g of x, and that's x squared, let's see, is x squared plus 1, right? So can I add these two functions like I add numbers? Yes. So the notation for it is f plus g, of x, like that. And what does that mean? It means f of x plus g of x, which means what? Take f of x, and add it to what? G of x. So we are adding the outputs, right? For the same input, we are adding the outputs. Make sense? It's the same input. So basically what we are doing is we are putting these functions like that, and then we are giving them the same input, and then for the output, we're going to take this. This is f of x, and this is g of x. So we are adding them, and then we get the sum. Okay? So now we can also do subtraction. Now before I do that, let's say for example, what is f plus g of 1? Well, that would be, according to definition, is f of 1 plus g of 1, which is what? Well, f of 1 is 1 plus g of 1 is 2. So the answer is 3. But we could also use this function, because now we have what? We have a new function, which is f plus g of x, and the formula for that function is x plus x squared plus 1. I know they're not in order, but doesn't matter. So we could also do this. When somebody says what's f of f plus g of 1, we could just substitute 1 here in this, right? And notice that we get the same answer, is 3, right? So that's how we apply these operations to functions, and they all have notations. So f minus g of x has this notation, and it means f of x minus g of x, and f times g of x has this notation. That means f of x times g of x. Multiply the two functions, right? Times g of x. And then f over g of x means f of x divided by g of x. And g of x, of course, cannot be 0. We can never have denominator of 0. That's the idea, okay? And so let's talk about these operations. So it says just create these functions and find the domain of these functions. Now the domain of these functions is basically the intersection of the domains of the two functions. So the domain of, let me write it here. So the domain of f plus g is basically the domain of f intersect domain of g. That means what they have in common, right? Because whatever x is, it has to work for both of them. If it doesn't work for f and only works for g, then we can add them. So basically you have to get the intersection. That means what they have in common, domain of f and domain of g. Now the domain of f minus g is the same thing. It's the domain of f intersect domain of g. The same is true for domain of f times g. Is the domain of f intersect domain of g. Now the domain of f divided by g is going to be what? Is going to be a set. Let me write it this way. So is x such that x is in the, this means belongs to. So x is in the domain, is in the intersection of the two domains, right? And also x does not make g of x 0. So that's kind of a set that we have to have. Now, usually instead of thinking of these, we just write the formula, we don't simplify it, and find the domain of what we have before we simplify it, right? So let's do that. So here, these are the two functions, right? So what is f plus g of x? So f plus g of x is going to be what? So f plus g of x is going to be, well, f of x plus g of x. This is f of x, this is g of x. We add them, we get that. The x squared goes away. And even if you don't simplify, the domain of this is still all real numbers because we don't have any restriction, right? No restrictions here. Now, what is f minus g of x? Well, it's f of x minus g of x, which is that minus that. Even if you don't simplify, this is still all real numbers, right? There are no restrictions. So we simplify and we get that. And what is f, this was a minus here, f times g of x. Well, that's f of x times g of x, so that's that times this times that. And before even we simplify, the domain is all real numbers, then we can simplify and write the domain. Okay, f over g of x is different because f over g, the domain here, right here, before we simplify, if possible, for right now there is no simplifying, but domain is not all real numbers because this denominator cannot be 0. So that means 6 minus x squared, we set it equal to 0. We solve this equation, right? This is 6. So that means x squared equals to 6. So x is plus and minus what? Square root of 6. So that means the domain cannot have 6 in it. I mean, square root of 6. So this is the square root of 6. And this is negative square root of 6. So everything is good except these two numbers, right? Everything to the left is good. Everything in the middle is good. And everything to the right is good. And that's how you write that. Or you can write the domain is a set like this, such that x is not plus and minus the square root of 6. Right? That's another way to write it. So that's 5. So let's do a few more. Let's do number 12. So in number 12, it looks like we don't have a good view. Let's do the web layout. Maybe we get it. So number 12. Okay, right here. So in number 12, it says use each pair of functions to find this. Now, this is what we call composition. So what is composition? Well, composition is something we only apply to functions. So we had these operations. These operations can apply to numbers and functions. But this composition has a notation. It's like a little, it's not 0, it's not O, it's just a composition symbol. So when I write f compose g, you can put parentheses here, and then of x. So it's f compose g of x. That's how you read it. F compose g of x. It means you take g of x and make it an input of f of x. And if you switch these, g compose f of x, it basically means take f of x and make it an input, make it the input of g of x. For example, if we have f of x equals to, let's say x, make it simple, and g of x equals to 3x minus 1, something like that. So what does this function do? This function takes x and gives you what? Gives you, let's make it 2x, so it's not just itself. So it gives 2x, so this is f of x. And then this one, what does it do? Well, it takes input and gives you 3 times input minus 1. That's g of x. So now when we say f compose g of x, what we mean is f of g of x. What does that mean? It means let the x go through g first, so that's g, 3x minus 1. Let it come out, and then let the output become an input of f of x. So this is f of x. So what do I do here? What do I write here? That's f, but it's f of g of x, right? f of g of x. So for example, if I put a 3 here, 3 times 3 is 9 minus 1 is 8. And 8 goes in there, 2 times 8 is 16, right? So f compose g of x is f of g of x, and the way we do it is, here is f, we take g of x, so this is g of x, right here. So we take this and put it here for g of x. So that would be f of 3x minus 1, and we know how to do f of something. That something becomes the input of f. So that would be 2 times, that's what f is, 2 times input, and input is 3x minus 1. So we just put 3x minus 1 here, which is going to be what? 6x minus 2, right? So that's our function f compose g of x. Now g compose f of x is going to be what? The other way around. So we're going to put f first, f comes out, and then let it go through g. So what comes out of here is what? This is f, and this is g. Now what comes out here is g of f of x. So now if we put the same input here, let's say 3. 3 goes here, and it comes out as 6. 6 goes here, 3 times 6 is 18, minus 1 is 17. So notice that g compose f of x is not the same as f compose g of x. In general, they're not the same. And the function will look different, because now we have to find g of what? Of what is f of x, which is 2x, right? And that is what? Let me write it here. Oops. So this was a box here. So this was g of f of x. Okay, so what is that? So g of 2x. So we have to take 2x and put it in g. But what does g do? G takes 3, takes the input and multiplies it by 3 and subtracts 1. And the input is supposed to be 2x, so put 2x here. So that's 6x minus 1. They're not the same functions, right? They're two different ones. So g compose f and f compose g are two different functions. Okay, so now that we know how to do this, let's do an example. So we want to do number 12. So number 12, this is our f of x and this is our g of x, right? So our f of x is x squared plus 1, and our g of x is square root of x plus 2. Okay, now we want to find f compose g and g compose f, right? So f compose g of x is going to be f of g of x. And so that means f of, what's g of x? Well, g of x, let's not confuse these. We're not doing these, right? Is up there, we're talking about. So g of x is the square root of x plus 2. And f of x is x squared plus 1. So f of x is something squared plus 1. And that something has to be square root of x plus 2. So that's x plus 2 plus 1, which is x plus 3. So that is our f compose g. And g compose f is g of, what is f? Well, f is x squared plus 1. So that means we have g, which is the square root of the input plus 2. And what is the input? Is x squared plus 1. So that would be, so we put x squared plus 1 here, and we simplify, we get x squared plus 3. So this is g compose f, and that is f compose g. All right, let's do one more of these, and let's do number 18. There we go. So it says find, this time it says find the, what are we supposed to find? We are supposed to find f compose g compose h. So is there 3 functions, right? What does that mean? Well, this means f of g compose h of x, right? And we know g compose f of x, h of x is g of h of x, right? That's what we want to find. So that means first we have to start from here. We have to put h of x in g and then see what we get, and then put that in f, right? So let's find the inside here first. So what is g of h of x? Well, what is h of x? H of x is square root of x. So h of x is square root of x. And then g of x is just x minus 6. So this is basically g of square root of x. So it means what? It means that I have to take square root of x and put it in g. G is x minus 6, so it's input minus 6. So it's the square root of x minus 6. So square root of x minus 6 is our g of h of x. That's it. So this is what that is. Okay, now we have to do f of that, right? Square root of x minus 6. But what is f? Well, f is right here. F is x to the 4th plus 6, right? So f is what? As x to the 4th plus 6. But what is to the 4th? That. So there. So that's the answer that we get for composition of those 3 functions, right? Okay, so let's do number 20. Let's do number 24. Now again, to find the domains of these things, all you do is just do it and don't simplify it. Find the domain and then simplify. So here we want to find what's q of x over h of x, and this is q of x, this is h of x, and state the domain of each. So let's write it here. So q of x is 1 over square root of x, and then h of x is x squared minus 9. So what is q of x divided by h of x, which is really what? Q over h of x, right? So we are just dividing the functions. So what we get is, what's q of x? 1 over square root of x, and then h of x is x squared minus 9, right? Now, before I simplify, I need to find the domain. Now notice that we have two denominators and we have this square root. We know that x can't be 0. Why? Because this denominator cannot be 0. Also, this is the square root of x. That means x has to be greater than 0. Can't be equal to, because we know it can be equal to. So that's that. So this denominator and this radical gives us these two. So x cannot be 0. That means 0 is no good, right? 0 has to be empty. Everything else is good. This one tells us that x has to be greater than 0. Again, 0 is no good. In fact, you can include that. Just let's do them separately. So do this. The square root gives us this condition. So let's just fill it in. Let's do it this way is better. So square root gives us this condition. The fact that it's in the denominator gives us this condition. And this denominator is another denominator that cannot be 0. So x squared minus 9, let it equal 0. Then we want to find, we say x squared is 9. So x is plus and minus 3. So that means x cannot be negative 3. Right? It has to be, oops, put it in the wrong place. So let me put it over here. Get my pen back. So let me put it here. So here is 0. So that means x can be 3 and cannot be negative 3. Now the question is, what do all of these have in common? What do all of these have in common? And if you think about it, now remember this one, let me get my pen back. So this could be any number except those, right? The denominator says could be any number except those. So what do they have in common? This condition comes from this denominator. This condition comes from the square root. And this condition comes from this denominator. They cannot be 0. Okay, so now, what do they have in common? Well, it looks like they have this part in common, and then also, so all of these are good, except for that number right there, right? 3 is no good. That makes sense? So that means 3 is no good, but anything to the right of it is good. Then union, this part right here is all the numbers between 0 and 3, right? So all the numbers between 0 and 3, 3 we know is not there, but 0 cannot be there either because it's not here, right? And that's it, because there's no more numbers on this one, so we cannot consider the rest of this because it has to be in all 3 places. So the domain of this is given by that. Oops, I erased it. Here we go. Okay. All right. Now, what about q of h of x? Well, I let you do that. I let you do these two. I did one of them for you. It's very similar. Don't simplify and then find the domain. Okay? Don't simplify and find the domain. All right, so let's let me do another one. Now if you are given, I'm just going to do one with the graph. So if you are given something with the graph, let's see, from here, number 42. If I want to do f of g of 3 and I have graphs, then I have to go to g. Let's say this is f, this is g. So I go to 3 and I go to 4 right there. You see g of 3 is 4. Put a 4 here. So f of 4 is 0. That's how we do those. Okay, so this is the end of this video. So what I'm going to do, I'm going to come back here and say bye to you. I hope you're doing well again, and take care of yourself and others. So I'll see you in the next video.